So hello everyone. I think everything is explained by Professor before, so I will explain the same thing. And the most important thing is that exciton. That in this case we study the dynamic of the exciton, that is the electron hole pair, and we need all the input files that we used for the in the previous meeting. And here is the summary of that input files, and there are the 5 input files and the RRR file, energy pop file, master optic file, band out file, and the MATLAB code. And we need to make sure that all the files have the same same number of lines. So we use in the same folder with the MATLAB code, and then we need open the MATLAB code, and we need to make some changes in the input parameters. So these are the some parameters that we need to change: time step, min, and omax, and the homo, and then the z step that we can calculate from that we can see from the band out file, and then the z size from the postcard file. So these are the input parameters that we need to change, and these this is the code that can be used to calculate the time integrated emission. And these are the equations that are explained by the professor, in which we use the one is time resolved emission and one is time integrated emission. So this is my model that I use for this calculation, that is the CNT with some defect, and that is the normal relaxation with initial condition, in which the yellow line represent the charge density of the photoexcited electron, and the dotted line represent the average energy of electron. And then this is the simple excitation of the um, excitation energy, how it changed with the time scale. So it is dynamic of the exciton energy dissipation with time, and the color range from the red to the blue, and red is the maximum population and blue is the zero population, and if it is the yellow, so it's mean it is in between the range. And this is the emission time resolved emission spectra, and this is the time integrated spectra. So we calculate the time resolved emission in the excited state, that is based on the presence of inverse occupation along the excited state trajectory and intensity of the oscillator strength. And the time integration is just simply the time resolved emission along the trajectory. So these are the results. That's it from my side. If you have any question, feel free to ask.
Okay, please join me in taking a part. So, any questions or suggestions? Like as a practical manual, is it clear? Everyone of us can repeat it. Amara, I do have a couple of suggestions rather than questions.
Okay.
So for this figure, would you be able to learn from Joseph and give a number? What is the photoluminescence quantum yield for this model?
For this figure?
Yes. It's not available right as a number from this code. You need additional code that Joseph presented today.
Okay, maybe I missed that code, so I will go through that.
His presentation, maybe listen the recording and try to find quantum yield.
Okay, yes.
Let's go to previous figure. Maybe Dr. Hunt has questions to it. So, from either fundamental or practical side. So while we're still thinking if there are more questions, let briefly. There are specific features of the geometry of your model. So can you please bring your marker your cursor to the defect, to the small to this absorbed to the surface. Closer to the molecule on the model. Yes. So,
Yes.
so there are two carbon-carbon bonds that define this model, right?
Yes.
So right now, these two bonds are arranged in parallel to the tube axis.
Yes.
Would you be able to place them perpendicular to the tube axis or at some other different angle?
Yes.
Okay. Yeah. So it would be of very big scientific interest to change the orientation of the attachment points and see how the spectra and quantum yield would change.
Okay. Yes.
So it was not a question; it was just suggestion how to.
Yes.
Any additional questions to Amara? Let's count down. Questions 1, questions 2, questions 3. Please join me in thanking Amara when you